Hello everyone, this is Group 10 and today we are presenting a research called An Approach of Blockchain Technology to Electronic Voting. This is the table of content of our investigation. We are covering the important concepts and mechanisms used in our approach. Traditional voting has presented several problems in our society these days. There are inconveniences about insecurity, scalability, longevity, or slow processing. This is why we are proposing an e-voting system that can cover these issues, providing attack security, cost-effectiveness, and confidentiality. In this image, we are presenting our approach. The voter can submit his vote through a physical voting machine or a mobile voting application. This transaction is sent to the Ethereum network, and with the help of smart contracts, which are pieces of code, we can perform a secure and reliable e-voting system. Here, it is a sample code of an e-voting application made in Solidity programming language that, as we can see, it has the core functions of an e-voting process, such as add candidate or vote. What is Ethereum? Ethereum is considered by many computer scientists as a computer world, since it's a peer-to-peer network that allows multiple applications to be deployed, providing two significant characteristics: transparency and immutability. This image presents the structure of a sequence of blocks, as we talk in the whole semester. Each block contains the previous hash from the previous block, timestamp, nonce, and the transaction. This transaction is stored in a Merkle tree, which is going to be explained in the next slides. There are some other elements inside of a block that are shown in this picture, and this data is saved in a Merkle tree, so no one can modify this data. But we focus on the elements that provide immutability, for instance, nonce and timestamps that are used to prevent reply attacks. As I mentioned before, this is the tree used in blocks. Here, in the presented image, we can see that every leaf node is labeled with the hash of a data block, and every non-leaf node is labeled with the hash of the labels of its child nodes. This is the way the data is stored in the whole Ethereum network.
It's similar to other applications based on blockchain. A typical Ethereum network applies several consensus mechanisms for implementing a new block into the existing chain. It depends on what type of blockchain, permission or permissionless blockchain. For the public Ethereum network, it's a proof of work. Proof of work is a mechanism forcing evaluation nodes or miners to solve a problem. It's some computation to prove that they are eligible enough to add a new block to the chain. Particularly, it's an attempt to use a hash function to find out value satisfying some condition. For example, in the public Ethereum network, valid values must have a fixed number of fixing zeros, and the network will reward the first miner who found out the valid value and amount of money. Is the Ethereum money in the Ethereum network or Bitcoin in the Bitcoin network? The difficulty of the problem is proportional with the length of the chain. For this situation, to increase the difficulty of the problem, the Ethereum network will require that return values must have more and more with fixing variables. This is to restrict the number of miners who want to participate in the network when the data chain become longer.
Having said that, the private key is first generated from a cryptographically secure pseudo-random number generator. Private key is a random 256-bit number within a desired range less than a specific constant big number. Again, the private key is an arbitrarily unpredictable and non-deterministic number, so the exact method that we use to pick that number does not matter as long as we reserve these two characteristics. Next, the public key is calculated based on the private key using the elliptic curve digital signature algorithms, which is called the SECP 256K1 standard. It is an algorithm based on the discrete logarithm problem expressed by addition and multiplication on the points of an elliptic curve. The public key is the result of the elliptic curve multiplication between the private key and the generator point. The generator point is defined as a constant point as part of the SECP 256K1 standard. The elliptic curve multiplication is a one-way function. It is easy to do in one direction and computationally infeasible to reverse. The hash functions are intensively used in almost all cryptographic systems. Therefore, it acts an important role here in Ethereum as well. So far, we have seen various implementations of cryptographic hash function in Ethereum blockchain, such as we have transforming public keys into addresses, unique identifiers, proof of work puzzle, data integrity, authentication as password hashing, and key stretching, pseudo random number generators, and it is resistant to the second pre-image. Specifically, the Ethereum uses a cryptographic hash function called the KK256, which is computationally efficient, is sensitive to any change in the message, and it is pre-image resistant as well as collision resistance. So the resistance to the second pre-image is primarily important to prevent digital signature forgery in Ethereum. In Ethereum, there are two types of accounts, also known as the wallet address, which is used in cryptocurrency application. One is called external owned account, specifically reserved for the user and represents as the user unique identifier. The second one is called smart contract, which represent for the unique addresses of the decentralized application. Both external owned account and smart contract has their own private key and public key. The generation of this key guarantee the strong cybersecurity of the Ethereum technologies. Here once again we observe another implementation of the KK256 hash function in the formation of the wallet address from the public key. The wallet address is a unique identifier derived from the last 20 bytes of the KK256 hashing on the public key. They are represented at the raw hexadecimal without any checksum. The rationale of this is to preserve the abstraction for the higher levels, whether the checksum can be added if necessary.
Now I would like to discuss about the advantages and challenges of our approach. First, for the advantages is immutability. It literally means that once a block has been added to the chain or a smart contract has been deployed, no one will be able to modify it. Second is democratized. Anyone can spectate the blockchain network, thus making it transparent. It is not owned or controlled by anyone. Third is reliability. There is no central point of failure in the blockchain network, as it is a decentralized application, and so it is protected against fraudulent activity and even in an apocalyptic scenario. Also, it cannot never be switched off. For the challenges, first is the human error. The smart contract is programmed by humans, so bugs or oversight can lead to unintended adversary action. Blockchain itself is a very complexity technology, so it may be hard to implement or understand it properly. One of the biggest problems of blockchain technology is scalability and performance, as it's always slower than centralized database. Every blockchain transaction must be digitally signed and verified using a public or private key cryptographic scheme, thus consume more time. The 51% attack. If more than half of the computers in the blockchain network agree to a term, and even if that term is a malicious term, it will be considered the truth. Now for the conclusion of our presentation. With this presentation, we want to introduce an approach that using Ethereum, an application developed based on blockchain technology to solve the problem of organizing a fair election. Also, we have made some analysis about the approach and the benefit that it brings to literacy. Blockchain itself is a very big topic, and we regret that we cannot cover every aspect of it. And thank you everyone for listening. Now it's the Q&A.